Welcome to module 32 of database management systems. From the last module we are discussing about transactions and transaction management, and we have taken a look into the basic concept of a transaction, the transaction state and the issues in concurrent execution. And in this module we will try to understand what are the very specific issues that happen when two or more transactions work concurrently. We have seen that it is possible that they execute in a schedule which would not let us preserve the ACID properties. So, we want to introduce the very basic concept of making sure that such concurrent execution schedules are acceptable, and those are the notions of serializability, and we will analyze different conditions called conflicts that need to be honored to attain the serializability of the schedules. So, serializability is the main topic to discuss. So, to understand serializability, we make a basic assumption. We make an assumption that every transaction by itself preserves the database consistency. That is, it starts in a consistent state of the database, and through the execution of its instructions in the order given, it leaves the database in a consistent state. That is satisfied in each and every transaction. So, we can conclude that if we serially execute a set of transactions, then the consistency of the database will always be preserved. Now, the problem happens, and as we have seen in the last module, that problems happen when possibly concurrent transactions happen, and we may be executing the instruction in an order which leads to the violation of ACID properties, the consistency in particular. So, we say that a concurrent schedule is serializable if there is some serial schedule. What is a serial schedule? Serial schedule is where the transactions are executed one after the other. So, if you have two transactions in the concurrent system, then if I do T1 then I do T2, it is a serial schedule. If I do T2 and then I do T1, it is a serial schedule as well. So, if I have a concurrent schedule, like if you refer back to the last module, schedule 3, where the instructions of T1 and T2 are interleaved, then it will have to be equivalent to a serial schedule, either T1 after T2 or T2 after T1. Different forms of schedule equivalence is used. One is called conflict serializability and the other is called view serializability. In the present module, we will first discuss conflict serializability. Now, a transaction may have all varied kinds of instructions, but we make an assumption that we will ignore anything other than any instruction other than the read and write instruction, because other operations, like we saw an operation where an account is debited by 50 or account is credited. So, you subtract 50, you add 50, you multiply by 0.1 or things like that, are all operations that happen in the local buffer in the memory and are temporary in nature, and mostly they do not affect the state of the database, because you have read the data, do the changes, write it back. So, it is a read and write that actually are important for the maintaining the consistency of the database. So, that simplifies our process of analysis to a good extent. So, we assume that between every read and write or read and read, write and write and so on, the database, the transactions may be doing arbitrary computations which are all in the local buffer and do not affect the state. So, we can make this assumption that our schedules consist only of read and write instructions. Now, we say that suppose II and IJ are two instructions for belonging to transaction Ti and transaction Tj. So, there are two transactions Ti and Tj. Ti has an instruction II, Tj has an instruction Ij, and we say that II and Ij, this instruction will conflict if and only if there is some item q, that is some data entity q, which both II and Ij are trying to access, and at least one of these instructions try to write. So, these two instructions from two transactions are trying to manipulate the same data item, and at least one of them is trying to write. If that happens, then we say that II and IJ, these two instructions are conflicting. So, you can naturally enumerate the four possibilities. If both of them are reading their own conflict, if it is read, write, write, read, write, write, all of them are cases of conflict. So, naturally intuitively you can figure out that since a write changes the value, if there is a conflict between these two instructions, then there must be a fixed temporal order between them. So, if II and IJ are consecutive in a schedule and they do not conflict, then we can interchange the temporal order of II and IJ. That will also not make a difference, because they do not conflict, but if they conflict, I cannot make the change in their ordering. So, that gives rise to the notion of conflict serializability. So, we say if a schedule S can be transformed into another schedule S primed by a series of swaps of non-conflicting instructions, then S and S primed are conflict equivalent. So, what are we saying? That we have one schedule S and we will swap non-conflicting instructions, possibly non-conflicting instructions that occur side by side, and if by doing this, if I can create the schedule S primed, then I will say S and S primed are conflict equivalent. But if S and S prime are such that I cannot transform S into S prime by just swapping non-conflicting instructions, then they are not conflict equivalent. The second definition to keep in mind is a schedule S is conflict serializable if it is conflict equivalent to a serial schedule. What is a serial schedule? Just to remind you, serial schedule is one where the transactions happen one after the other in a serial manner. So, all instructions of one transaction complete, then all instructions of the second transaction complete, then all instructions of the third transaction complete, and so on. So, if a schedule is conflict serializable, that is, if in a schedule I can swap non-conflicting instructions and make it into a serial schedule, then I will say that the given schedule is a conflict serializable schedule. Okay. So, now let us, it is time for a number of examples to understand this better. So, we had seen schedule 3, you will have to refer to the earlier module for schedule 3. I am sorry, this is this is just abstracted form of that, not the actual one, because in the earlier schedule 3 we had shown all the other computations also, but the read writes are the same. Now, that this schedule 3 can be converted to, so this is where you have schedule 3, and you can easily see that it is a part of transaction T1, then a part of transaction T2. So, schedule 3 is not a serial schedule, but if you can swap non-conflicting instructions, then you are able to convert this into this schedule, which we are calling as schedule 6, where all instructions of T1 is followed by all instructions of T2, which is a serial schedule. So, since this can be done, we will say it is conflict serializable. Schedule 3 is conflict serializable. And just to see how that happens, so you start here, let me erase these marks and start here. So, here if I look into these two instructions, which are the consecutive instructions in schedule 3, I can swap them. That is, I can do read B first and then do read A. I can swap read B and write A. Read B and write A can be swapped. Once I have done that, then I can swap read B with read A. It has become before write A. I can swap it with, because read B and write A or read B and read A, these do not conflict, they are non-conflicting instruction. Why read B and write A are non-conflicting? Because they are not reading and writing to the same data item. Why read B and read A are non-conflicting? They are accessing the same data item, but both of them are read, there is no write. So, I can swap. So, this is the second one I can. So, once I do that, read B will come here and read A, write A will come down. Then again I can see that write B can be swapped with write A, both are writes, but referring to different data items. Similarly, write B then can be swapped with read A, because they are again referring to different data items. So, I can do this, and then these will also come up. So, I will eventually, after these 4 swaps, this whole schedule 3 will transform into this schedule 6, and we get a serial schedule. So, we will say that schedule 3 is conflict serializable. That is the basic concept that we are trying to establish here. Just as very simple example, suppose you had 2 transactions T3 and T4, and you have this situation. Now, is it conflict serializable? It is not, because to make it conflict serializable, I need to either swap write Q of T3 with write Q of T4, which is not possible because these are conflicting instructions. They both access the same data item Q and they both are write. The other option is I could swap read Q in T3 and write Q in T4, that they are also conflicting because they access the same data item and one of them is write. So, I cannot do either of these swaps, which mean that I cannot find a conflict equivalent schedule for this schedule either to T3 T4 or to T4 T3. It is not, this schedule is not conflict equivalent to either one of them. So, this schedule is not conflict serializable. This is the core concept. So, if you go through different examples and try to understand this at the very beginning, then in terms of the transaction management, the whole study of transaction management, you will have very easy progress. So, let me show you number of other bad schedules and let me little bit more complex examples. So, consider 2 transactions, transaction 1 here update an account where the account ID is 31414, a specific account, and balance is debited by 100. So, it is debiting 100 from the balance. When in transaction 2 you update accounts where balance is changed to balance times 1.005, which means that you are giving a 0.5% interest, and here there is no where clause. So, transaction 2 actually does this balance change in all the accounts, whereas transaction 1 makes this debit in only one account. Let us see what will happen in terms of them. So, let us first try to write out transaction 1 and transaction 2, the first in the read write abstracted form. So, transaction 1, it is working only on one account, let us call it account A. So, what does it do? It has to set the balance to debit 100. So, it has to read. So, this is R1 by R1 A we mean that it is read, the subscript here refers to the transaction number. So, R1 stands for R stands for read, 1 stands for transaction 1. So, it is read by transaction 1, and what are we reading? We are reading the account balance A. Let us arbitrarily we are calling it A. And then what we will have to do after having debited that locally, we will have to write it back so that the changes happen. So, R1A followed by W1A is transaction 1, which is being shown on the left. So, I have shown you from the actual SQL statement how can you make an abstraction of the read write that we use in terms of reasoning about the serializability. In contrast, if you look at transaction 2, naturally transaction 2 does not have a where clause. So, it performs this balance update on each of the accounts. So, it will also perform this balance update on the account A or account balance A rather that we assumed in the transaction 1. So, we model that by saying that naturally for changing the balance from balance times 1.005, we need to read A. The read is done in transaction 2. So, that is R2A and write it back. So, that is W2A, and then he assume that B is some other account. There may be one more account, there may be 100,000 more account, but so far as serializability are concerned, these are all other different accounts from A. So, we symbolically just consider one, that is some other account B other than the balance A, and naturally to do the change here or do the update here, we will have to read B, R2B and W2B. So, these are the two transactions in the simplified form that we have to analyze. Now, let us consider so we have between transaction 1 and transaction 2, we have 6 instructions. So, we produce a schedule 6 where these 6 instructions are interleaved, and we satisfy the basic constraint that the instructions of every transaction occur in the same order in which they existed. So, R1 precedes W1, R1 precedes W1 in this schedule, R2A precedes W2A, W2A precedes R2B, R2B precedes W2B and so on. So, their original ordering is maintained, but we have an interleaved schedule called S. And then on the right, if you look at here on the right, this is schedule S. So, in the right we are saying that let us say that A starts with $200 and B at the beginning is $100. So, what will happen? You will read here, this is the first thing, R1A. So, 200 is read, then R2A. So, what happens if R2A is read? Again 200 is read, and then you do W1A. So, what is W1A? W1A is the write of the transaction 1. So, transaction 1 writes after debiting this balance. This is the intermediate computation. So, when transaction 1 writes, it writes based on the value that it had read in R1A, which was 200, then 100 debited. So, it writes back 100. Then the next is W2A. So, W2, what will W2A do? W2A will write back the W2A is here, will write back the result of the computation in transaction 2 based on what it read in the R2A. R2A had read 200 here, and therefore, if you multiply 200 by this factor, it becomes 201. So, W2A will write 201. So, naturally, as W2A has changed the value of A after W1A, naturally the final value of A will be 201. Then you have R2B, W2B, which reads 100, makes this balance change by 1.005, it becomes 100.5. So, this is what we will have when actually this schedule completes. So, if just look at what has happened, it has I have debited $100 from account A, which was transaction 1, but and I had started with $200, but at the end what I have according to the schedule is account A has a balance which is $201, whereas it should have had a balance which should have been $100. The balance in account B is fine, but it shows that $101 more in account A. So, naturally the bank is going to get bankrupt very soon if such schedules are allowed. So, this schedule is an incorrect, inconsistent schedule, it is a bad schedule. Let us take other examples. Now, let us ask what is the ideal schedule? What is ideally what should happen? Ideally, naturally we can have we will have schedules. There are 2 transactions. So, there are 2 possible serial schedules that can happen, that is first T1 happens, then whole of T2 happens. I am sorry, first T1 and then whole of T2, or first whole of T2 and then T1. And if you go through the steps, assuming that A initially is $200 and B is $100, these are the possible results that you see. Naturally, as I had mentioned earlier also, the different ordering, different schedule might give you different results, but both of them are correct because any one of them will happen, but both are consistent. Either debit has first happened, then the interest credit, or interest credit has first happened and then the debit. So, either of these schedules are acceptable, but what we got as a schedule S in the last case is not acceptable. So, we will call a schedule serializable if it has the same effect as some of the one of the two schedules that we have here. Then we will say that this is a serializable schedule. So, again we create another example schedule T here. So, what we do, we take the schedule S which we saw was bad and we interchange these two. We do W2 for A first and W1A next. Now, you see very interesting things will happen. So, now you focus on this part, on the left part of schedule T, where we are assuming that A and B both have $100 to start with, and then go through these steps. R1 is in transaction 1, R2 is in transaction 2, then W2 happens. So, the interest is credited 100.05, and then what has happened, W2 after that W1A. So, whatever was written here is debited and written back. So, whatever was read there is $100. So, you debit $100, it becomes 0. So, A has become 0, and then you have the B which goes on correctly. So, things look like that. It appears that we are perfectly okay. So, by the first example, the outcome is same as a schedule 1, and so we might just think that things have been good, but this is just incidental based on the particular values. Now, let us consider another execution by the same schedule which makes use of this value 200 and 100. Now, as we do with 200 and 100 and we do W2 followed by W1. So, when R2A is followed by W2A, R2A had read 200 and that 1.005 or that kind of interest is given, then it becomes 201. And then R1, then you have W1. Now, what does W1A changes? R1 had read 200 and from that you have subtracted 100. So, now you have as W1A you have 100 input, and from this you have B certainly does not change. So, if you look into that, now you can see that A has a value which is 100, which certainly if you look back. So, 200 and 100 are the values that we had assumed here, and you can see that in neither of this schedule A can have a value which is $100 as we have found here. It can either be 100.50 or it can be 101, but you have got a value 100. So, even though with some data a schedule might look like serializable, but it as actually is not, and it needs to be properly established that a schedule is serializable. So, neither S nor T are serializable. Yet another schedule U, this again. So, you can see that transaction 1 is happening, instruction of transaction 1 is happening somewhere in the middle with transaction 2, and this is what you get. So, if you look back as to earlier case, you will find that this is same as schedule 2 101. So, this is same as schedule 2. So, again by the data it looks like that this is correct, but we have to actually establish that this is correct. So, we can establish that by proving that schedule 2 is schedule 2 is conflict serialized, schedule U is conflict serializable to schedule 2. How we do that? We keep on swapping the non-conflicting instructions. So, this is the one we start with, and we swap W1 with R2B, this is possible, they are referring to two different data items. Then we swap W1 with W2, again different data items. Then we swap R1 with R2, again different data items, and also they are both of them are read. And finally, we swap R1 with W2, R1A with W2B, and we get this. And now you can see that this is transaction 2 followed by transaction 1, which is schedule 2, which is indeed a serial schedule, and we have been able to transform schedule U into a conflict equivalent schedule 2, which is serial. So, we will say that while our earlier attempts on schedule S and schedule T were not serializable, schedule U is serializable. So, naturally, all serializable schedules are they conflict serializable? No. For example, here I have given. So, here what we are trying to highlight is a schedule may be serializable, but it may not be conflict serializable. So, conflict serializability is a stronger notion. So, here I have given a small example, which I will leave to you to go through in detail and understand, where it is not possible to show that it is conflict serializable, in the sense you cannot, there are 3 transactions here, W1, W2 and W3, and you cannot swap non-conflicting instructions in this schedule and convert it into a serial schedule. So, serial schedule here will mean T1, T2, T3, T1, T3, T2, T2, T1, T3, like that, any of the 6 possibilities. You cannot convert this in a conflict equivalent manner to any of those 6 serial schedules, but this actually is a serial schedule, because very interestingly, even though there are multiple writes, but in between there are no reads. So, you can easily reason that the values have actually not changed. Okay. So, this is on the basic notion of serializability. Now, the question naturally is, how do I detect if a schedule is serializable? So, the process is to construct a what is called a precedence graph. So, if I have a set of transactions, then I construct a graph. It is a directed graph, where the vertices are the transactions, their names, and we will draw an arc from T I to T j. That is a graph means there will be a edge, is a directed edge. If these two transactions T I and T j are conflicting. So, if T I T j conflict, there will be an edge between that, and the edge will be from T I to T j if T I access the data item which conflict with T j. So, if T I is ahead, is earlier, then we will draw the arc from T I to T j, otherwise it will be from T j to T I. And we may also annotate, label the arc by the item on which item that is being accessed. So, this could be a possible what is called the precedence graph. So, a schedule is conflict serializable if and only if its precedence graph is acyclic. Naturally, if there is a cycle, then that means that any of the like we have here, if it is acyclic like this, then it is possible that I can actually do a topological ordering of these nodes, and we can find a serial schedule. But if it is a cycle, then naturally I cannot put any of the transactions on the cycle at the beginning and put the others on the later part, things will obviously always conflict. So, you can easily, these are details of the algorithms, cycle detection can be done very easily, either in n squared time in a simple manner, or in n plus e time, where e is the number of edges. So, the precedence, if the precedence graph is acyclic, the serializability order will be obtained by simple topological sorting. I am not discussing what these algorithms are. I would expect that you know. If you do not, please look up in an algorithms book. So, to test for conflict serializability, the steps will be build the directed graph, then go through each operation of the schedule, look at each operation, read or write. If the operation is a write, then find, so if it is Wix, then find what is happening with this data element x in different transactions that exist later on, that instructions exist later on. If there is some rjx or some wjx, either in this was in transaction I, in some transaction j, if there is a read of x or if there is a write of x, then there will be a directed graph age from Ti to Tj. This is what I had said earlier. On the other case, if your operation is of the form Rij, if it is a read operation, then all that you need to look for is only a write on this x on the different transaction, and then you will have a age. Naturally, if your current operation is read and you do not find a write, there may be other reads on x, then you do not add any conflict edge. So, on this graph the schedule is conflict serializable if it is acyclic, and we will do topological sort to get that, as I have said. So, here what I have done is I have actually taken a little bigger example, where you can see that at the beginning here I have given a schedule which has 5 transactions, and it has A, B, C, D, E, 5 different data elements and variety of read write happening on them. So, based on that you start with an empty graph having, so your graph will have 5 nodes, because these are the transactions, and then you go through the schedule. You start with the very first one, W1A. So, A is the data item you are looking at, and then you see who is doing it. So, you see that, well, A is read by, A is here read by T2. So, there is a conflict. So, there is a conflict. So, you will add an edge T1, T2. So, this edge gets added. Then you have R2A, and you find, okay, look for A, there is no A. So, there is no subsequent write. So, there is no new edge. Then you have W1B, and if you look for, you have R4B. So, R4, that is transaction 4 is reading it later on. So, W1A, B is subsequently read by T4. So, there is a conflict. So, you add the edge T1, T4, T1, T4, right. You proceed in this way, you can work it out in full, and when you come to the end, you have constructed this particular graph, which is the precedence graph, and you can very easily see that this precedence graph is acyclic. There is no cycle here, and therefore, the original schedule is serializable. And what is that? What is the order in which you find out what is the corresponding serial schedule? For that, you do a topological sort. So, by topological sort, which will mean this have no predecessor. So, any one of them can be the first node, other one can be the next node. So, it could be T3 T1 or T1 T3. So, let us say T3 T1, then T3 T1 has happened. So, I can put any one of T2 or T4 after that. Here I have put T4, then T2. So, up to this, and then finally T5. So, this is one possible serial schedule to which this given schedule is conflict serializable. And so, the actual serial schedule. So, if you do this schedule, you will get a result which is a result of this serial schedule, which is T3, T1, T4, T2, T5. It is also actually this schedule is conflict serializable to several other schedules, because you can do this topological sorting in various different manners. You could have started with T1 and then do T3 and then do the rest. You could have done T3 T1 and then instead of doing T4 T2, you could do T2 T4. So, you will get a number of, but having one equivalent serial schedule, one conflict equivalent serial schedule is enough to prove the serializability of a schedule. Now, so based on that, you say that this particular schedule is conflict serializable, and it will be safe to execute the interleaved instructions of the 5 different transactions in this manner in the schedule, and we will always have a consistent result. So, here in this module you have understood the issues that arise in terms of concurrency when 2 or more transactions work concurrently, and very specifically we have learnt about different forms of serializability. In this module we have talked of conflict serializability, view serializability we will take up later on, and we have seen an algorithm, simple algorithm based on the acyclic precedence graph, which will allow you to ensure that a given schedule is conflict serializable or not.